So if you were to jump into a time machine, go back exactly 100 years to 1926, and ask the smartest minds alive what the most valuable resource on Earth was, they wouldn't even hesitate.
Where they'd say oil, black gold.
Exactly. This thick, messy liquid that literally built empires and sparked massive global conflicts. But if you look at the world right now, the ultimate global currency holding the entire economy hostage isn't liquid at all.
No, it's completely solid. I mean, it's essentially just modified sand.
Right, silicon. Which brings us to the core of today's deep dive. If you're obsessed with the why behind human success and the hidden forces running our world, you are absolutely in the right place.
Yeah, hit subscribe and turn on that bell to join the Insight Lab. We drop deep dives like this every single week to help you outsmart the average and see the invisible structures around you.
Now let's get into the data. Most people think AI getting smarter or cars getting way more expensive is just, typical inflation or natural tech progression.
It's really not.
No, it's not. Today we are breaking down the semiconductor siege. We're going to show you why your digital life, and frankly, the entire global power structure, might be completely reliant on a single fragile island.
Because we've totally transitioned from an economy constrained by what we can pull out of the dirt to one constrained by what we can print on a literal atomic scale.
Okay, let's unpack this. The comparison to oil is a great hook.
Yeah.
But the research shows that analogy breaks down pretty fast when you look at the actual supply chain.
Yeah, completely. Think about it. In the 20th century, if a nation ran out of oil, the effects were super physical. Tanks stopped rolling. Power grids just shut down.
A total physical standstill.
Exactly. But today, if a country gets cut off from advanced semiconductors, the physical world might keep spinning for a minute, but the future just stops dead.
Because without those chips, artificial general intelligence development freezes.
Right. And your power grids, which use these hyper-complex algorithms now just to balance loads, they become incredibly vulnerable. Whole sectors of the economy just stall out.
And the geographic distribution is wild. Like, oil is everywhere, Texas, the Middle East, the North Sea, but advanced chips.
Hyper-centralized, we're talking about the absolute bleeding edge of hardware, the stuff you need to train the newest LLMs.
And it's predominantly made by one single company, right? TSMC.
Yeah, Taiwan Semiconductor Manufacturing Company. And that intense centralization is what creates this modern siege mentality. With oil, you can just dig a new well somewhere else.
Right, you poke a hole in the ground.
But you cannot just dig for a 3-nanometer semiconductor.
Digging for oil is just poking a pressurized hole in the earth, but building a chip, a fabrication plant, is like trying to build a hyper-advanced space station here on Earth.
That's a great way to put it. It's like performing microscopic open-heart surgery in a room where a single speck of dust acts like a boulder that just crushes the patient.
The research says a state-of-the-art fab costs roughly $20 billion.
Which is astronomical.
It is. But here's my pushback. If the entire global economy knows this is the ultimate bottleneck for the AI arms race, why hasn't a consortium of countries just pooled like $1 trillion to build a faster alternative?
What's fascinating here is that $20 billion is literally pocket change for a superpower if it guarantees national security.
Right. So why not just build 10 of them in Ohio?
Because the true bottleneck isn't the money. It's the compounding complexity of the supply chain. You can't just buy extreme ultraviolet or EUV lithography machines off a shelf at a hardware store.
Well, let's actually look at the mechanics of those EUV machines because, honestly, it sounds like pure science fiction.
It really does.
To etch these atomic patterns onto silicon, they are shooting microscopic droplets of molten tin with lasers. Wait, really? Tin?
Yeah, molten tin. And they shoot each microscopic droplet twice. The first laser pulse flattens the droplet into, a pancake shape.
Okay, microscopic tin pancake. Got it.
And then the second, way more powerful pulse vaporizes that pancake into a plasma that burns literally hotter than the surface of the sun.
That is completely insane.
And that plasma emits the extreme ultraviolet light they need to etch the chips. Oh, and this happens 50,000 times per second.
50,000 times a second. And because EUV light is absorbed by practically everything, even air, this whole thing has to happen inside a perfect vacuum.
Exactly, which totally explains why you can't just onshore this overnight.
Right, because to reflect that light inside the vacuum, you need these incredibly flawless mirrors from Germany.
Flawless is an understatement. If you scaled one of those German mirrors up to the size of the entire United States, the highest mountain would be less than a millimeter tall.
Unbelievable.
Yeah, they use these alternating microscopic layers of silicon and molybdenum just to bounce the light without absorbing it.
So you need the German mirrors. You need these specialized Japanese chemicals that react to that exact wavelength of light. You need American software.
And most importantly, you need the human capital. You need thousands of engineers with decades of highly specific, tacit knowledge.
So you can't just throw $1 trillion at a field in the U.S. and expect to buy 20 years of intuition on how to tune a magnetic levitation system.
Exactly. You just have a really expensive, very empty building. And the lag time is the real killer.
Because while you spend 5 years building that fab, TSMC is already 2 generations ahead of you.
You're perpetually playing catch-up.
Here's where it gets really interesting geopolitically.
Yeah.
Because this massive bottleneck is located on Taiwan, it's birthed this concept of the silicon shield.
Right, the ultimate geopolitical deterrent.
Yeah, because if those factories were to just halt production from a blockade or an earthquake, global GDP drops by trillions of dollars instantly.
Within weeks, all consumer electronics manufacturing would shut down. Auto plants would furlough millions of workers. The cloud would start failing.
So this shield theoretically protects the region because a war there is basically economic, mutually assured destruction.
But that realization has caused absolute global panic.
Hence the massive push for tech sovereignty. The U.S. has the CHIPS Act. Europe is doing the same. China is subsidizing legacy nodes.
Nations aren't fighting over pipelines anymore. They're fighting over nanometer architecture.
But wait, if every major power is building these digital walls and trying to onshore production, doesn't that inherently destroy the globalized efficiency that made these chips possible in the first place?
If we connect this to the bigger picture, you aren't destroying efficiency. You're just redefining it.
How so?
Well, for 40 years, efficiency meant the cheapest cost per unit. Materials from Africa, optics from Europe, assembly in Asia.
Right, which kept consumer prices super low.
But the pandemic and rising geopolitical tensions showed us that hyper-efficiency is actually incredibly brittle. One blocked canal or factory fire freezes the entire world.
So now efficiency means cheapest per unit that won't get cut off during a global crisis.
Precisely. Building redundant fabs in the US or Europe costs way more, which means the chips will be more expensive.
And consumers will absolutely feel that checkout counterpain.
Oh, without a doubt.
But as much as everyone is fighting over these factories, the research highlights a massive plot twist. The Silicon Siege actually has a strict expiration date dictated by the laws of physics.
Yeah, we are talking about the absolute end of Moore's Law as we know it.
Right, the physical cliff. It sounds like we've been packing a suitcase tighter and tighter for 50 years, and now the zippers are literally breaking off. We don't need to fold things smaller, we need a totally different kind of bag.
Engineers have shrunk these nodes so much that the electrical pathways are literally just a few atoms wide now.
And when you get down to the atomic level, classical physics just gets weird.
Very weird. Classical physics stops applying entirely.
The research dives into quantum tunneling. From my understanding, the insulating gates that hold the electricity back, keeping it as a binary 1 or 0, are getting so thin that the electrons just ignore the wall.
That is exactly what happens. An electron behaves like a probability wave down there. So there's a non-zero chance it'll just pop through to the other side of that atomic barrier.
Just teleport through the wall.
Pretty much. And if you're training a massive neural network and stray electrons start flipping zeros to ones randomly, your AI suddenly starts hallucinating wildly.
You literally can't trust the math the computer's doing anymore.
The logic totally breaks down. The chip becomes fundamentally unreliable.
So all this money, these hundreds of billions being spent on silicon fabs, is for technology that's basically maxed out.
Which is why the future isn't just a race to build more silicon. The real race is a frantic scramble to completely reinvent what a chip even is.
And the industry is pivoting hard to next-gen materials. The sources talk a lot about carbon nanotubes.
Oh, those are fascinating. Imagine a single sheet of graphene, just a flat layer of carbon atoms rolled up into a microscopic, seamless cylinder.
And that structure changes how the electricity flows.
Dramatically. Electrons experience what's called ballistic transport inside that tube.
Meaning they don't bounce around and crash into things as much.
Exactly. They shoot straight through. In regular silicon, electrons scatter all over the place, which generates a ton of heat.
Which is why data centers drink enough water to supply a small city just to stay cool.
Right. But in a carbon nanotube, there's almost zero scattering. It conducts electricity way faster, generates way less heat, and you can pack them super tightly without melting the board.
The research also brings up gallium nitride. We already see this in those high-end phone chargers, right?
Yeah, GaN chargers. It has a much wider band gap than silicon.
Band gap being the energy needed to free an electron.
Exactly. Silicon gets leaky when it gets small and hot. Gallium nitride can sustain much higher voltages and temperatures without the electrons jumping the track.
So no quantum tunneling errors. But the true holy grail the research points to leaves binary computing behind entirely,
Quantum computing.
completely abandoning the on-off switches for qubits that can be multiple states at once.
Yeah, going to carbon nanotubes is just a materials upgrade. It's a better highway for the same binary cars. Quantum computing is a completely different universe of processing.
Which raises an important question. If a country successfully masters quantum computing at scale, do we actually solve the geopolitical siege, or are we just resetting the board for a new resource war?
A technological leap like that rarely eliminates competition. It just shifts the battleground. But true scalable quantum computing is an existential shift.
Because the power scales exponentially.
Exactly. Whoever gets there first could instantaneously break current RSA encryption. Every secure communication, every bank transaction on the classical internet becomes transparent to them.
So the silicon shield of Taiwan and all those trillion-dollar silicon fabs in the US and Europe would just become obsolete overnight.
It'd be like having a monopoly on the absolute best horse-drawn carriages the day Henry Ford rolls out the Model T. The infrastructure you spent decades protecting just doesn't matter anymore.
Wow. Okay, so what does this all mean for you listening right now? We've talked about billion-dollar fabs, laser vaporized tin, quantum tunneling. It feels abstract.
But just look at the phone in your hand.
Right. Instead of just seeing a screen for your apps, we want you to use the Inside Lab protocol. It's a mental check you can do tomorrow.
We call it the supply chain lens.
Whenever you look at a piece of tech, run it through this 3-step check. First, acknowledge the physical materials, the silicon and the rare earths. Second, trace the human genius, the German mirrors, the Japanese chemicals.
And third, recognize the fragility. That device only works because global peace is holding that complex network together today.
This protocol isn't just trivia. It's the tool you need to decode the news. When you hear about tariffs or AI regulations, you now know there's a global siege happening every day just to keep the pixels firing on your screen.
You're actually seeing the microscopic mechanics behind the headlines now?
But if you realize today that silicon is basically a maxed out trap, you are only halfway there. Because the real war isn't over what we have now, it's over what replaces it.
The race for quantum supremacy.
Exactly. Watch our breakdown on the quantum computing race right here to complete the puzzle and see exactly who is poised to break the silicon shield first. Keep questioning the why behind your world, and we'll see you in the next deep dive.